So vector algebra part 3, and we have two recordings of part 3A, part 3. Today first we will see multiplication of vector by a scalar. Multiplication of vector by scalar. So actually when we have any vector, suppose vector A, this is a vector A, and lambda is a scalar. Lambda is a scalar. When we are multiplying the scalar with the vector, we can write because the scalar has nothing to do with the vector. It will multiply with the magnitude of that vector. For example, lambda A, if you are multiplying lambda with vector A, so this will multiply with its magnitude. For example, if lambda is 2, this will become, suppose lambda is minus 2, then it will become minus 2A. For writing the magnitude also, you can either write their separate magnitudes, or you can write lambda A, magnitude of lambda A, or you can write their magnitude separately because they are the scalar quantity. So scalar lambda is also a scalar, and its magnitude of this vector is also a scalar quantity. So scalar and scalar multiply to get the scalar quantity, that is the magnitude. Okay, so this is just simple multiplication of a. That means for any vector, for a value of lambda, the vector lambda A, just this is very important. For any value for any value lambda, vector lambda A, vector lambda A is always collinear to this vector. Lambda A is always collinear to this, to the vector A. The vector A. These are the collinear properties of multiplication of a vector by a scalar. You can multiply subtraction in multiplication. Suppose lambda will multiply with vector A plus vector B. So we can separately multiply them. We can get lambda A vector plus lambda B vector. And if it is minus also, the same thing will happen with minus also. And in multiplication, you have to multiply any vector. Then one thing I told you before also, then I will explain component of a vector. So component of a vector So for component of a vector, you can see that this is three-dimensional. We are just having three dimensions. Here, this is suppose you have x-axis, y. So this is suppose your y-axis, and this one is your x-axis, and on z-axis, and this is your x-axis. Suppose this we are taking x-axis, and this we are taking as y-axis, and this is your z-axis. Okay. So if P is a point here, so when you draw a perpendicular on x-axis, y-axis, and z-axis, so when you will get the perpendicular at this point, suppose here, so this will be your y distance because this is y-axis. So y coordinate is the distance on y-axis of the perpendicular from this point in 3D. And when you draw perpendicular at this point, this distance you will get z. And similarly, we cannot show here somewhere on x-axis, you will get the distance. This is the x coordinate. So always a point is denoted by the three coordinates x, y, and z in 3D. Okay, but this is y. Y is a scalar. If you want to make it a vector quantity, so you have to multiply with its direction. So in y-axis, this vector y, this part, you can say this is suppose a o, and this is a b, and oc. Okay, so vector, what will be vector ob? Vector ob will be ob vector, because I cap, you know that I cap, j cap, and k cap. I is the unit vector along x-axis, j is the unit vector along y-axis, and k is the unit vector along z-axis. So OB will be equal to y times j, because this is along y-axis. This is y-axis. Okay, this is along this one is y-axis. That's why OB vector will be equal to I j cap j. This is called the component along y-axis. Similarly, along x-axis, OA is the component of this vector. Which vector? We are considering this vector O to P. OP is what? Is a OP is a position vector. So this position vector can be resolved into three components. So vector OA will be equal to xi, and OC will be equal to zk. These are the components. So when it is resolved into three components, then separately these are three components along x and y and z axis. And generally, this vector, position vector of any point, we are denoting by vector r. So OP is the vector r. So vector OP, in terms of resolution of the components, it can be written as xi plus yj plus zk. So this is called the resolution of components. Now, this OP vector, it can be written as vector R also, I told you that. So what will be the magnitude of this vector when it is resolved in component, means I, J, K direction. It is resolved into three directions, I, J, and K, any x direction, y direction, and Z direction. Therefore, its magnitude will be under root of x square plus y square plus z square. This will be the magnitude of this vector. Okay. Okay, got it. Now we have some questions on this one. You can take the screenshot if you want. You can take the screenshot so that I can go to the next page. Clicking this page. So now we have a question. If suppose if vector A is equal to 2i 2i plus 3j plus 4 plus 4k. Then find its scalar and vector component. Find its scalar and vector component. Scalar and vector component. Okay. Components. I told you components. Huh? So scalar components are. Can you tell me what are the scalar components? So here scalar components are scalar components. Component there are 2, 3, and 4. These are the scalar components. And vector components are 2i, 3j, and 4k. When they are asking only components, we can do like, okay, then this is for example number 1. We take example number 2. Take example number 2. Find a vector in the direction of vector. Find a vector find a vector find a vector the direction of vector A is equal to vector A is equal to I minus 2j I minus 2j that has magnitude 7 units. That has magnitude 7. Okay. So we have to find the vector in the direction of vector A. And if you have to find any vector in this direction, you have to find the unit vector. And unit vector A, always unit vector of any vector you have to find you can divide the that vector by its magnitude. Vector divided by its magnitude, you will get the unit vector. And what is here? Unit vector is I. Here vector is I minus 2j. There is no k here. Divided by under root 1 square 1 and 2 square is 4. So under root 5. So you are getting the unit vector as, you can write 1 by root 5, 1 by root 5I minus 2 by root 5j. This is unit vector. So unit vector means it will give the direction. Unit vector means it has magnitude 1. If you will find its magnitude, I am talking about the magnitude of this one. This one, magnitude of this one. This is a unit vector. I, this is j. Okay. So if you find the magnitude of this vector, that will come 1 because it is a unit vector. It is converted into unit vector. Unit vector means which has magnitude 1. If you want to give the direction of any vector, you have to multiply, and that has a magnitude, suppose here 7 units. If you will multiply with 7, so this will get the magnitude as 7 because here magnitude is coming 1. Therefore, the vector having magnitude and in the direction of A will be 7A. Okay, got it? So we can say that vector having magnitude, vector having magnitude, having magnitude 7, 7 units, having magnitude 7 units, and in the direction of A, and in the direction of A, the direction of vector A. This will be equal to 7 into multiply with unit vector in the direction of A. Unit vector is always denoted by cap. So 7A. So this you will multiply by 7, you will get that means 7 into unit vector A. Unit vector A is I by root 5 minus 2 by root 5j. Or you can write 7 by root 5 I minus 7 to the 14 by root 5j. So this is the unit vector in the direction of vector A, which has magnitude 7 units. So like this, we can find out that any vector in any direction which has different magnitude. In the same direction of this vector, we can find any vector which has different magnitude. Okay, its magnitude is different. This vector has magnitude under root 1 square plus 2 under root 5. Magnitude of, what is the magnitude of this vector? This vector A is equal to I minus 2j. Its magnitude is under root 5. Okay, then make this magnitude 1. So for that vector divided by its magnitude, so it will become, then its magnitude will become, this is a unit vector. Okay, so this j, it was not clear. Now like this, we can find any vector in this direction. So if you want, you can take the screenshot, otherwise going to in component forms, that if you want to add and subtract, their ijk component will be added. So for component form, suppose A is a vector, its component are suppose A1 I plus A2 J plus A3 K. And there is another vector which is resolved into the components B1 I plus B2 J plus B3 K. So you can add, subtract, multiply, equate. So what will be the condition? So addition subtraction is simple. If you want to add or subtract, their I component will be added in I obviously. So therefore their addition or subtraction, if we add or subtract them, so we can write I components together. So A1 will be added in B1 or subtracted in B1 I plus A2 plus minus B2 J. I'm writing together both the properties, and B A3 A3 plus minus B3 K. So like this, we can add and subtract their components, and similarly, if they are equal, we can equate their components. है ना? Suppose A is equal to B. Suppose A is equal to B. We have given that suppose vector A is equal to vector B. So that means their components are equal. So we can write, this implies that we can say that we can equate A1 is equal to B1 and A2 will be equal to B2 and A3 will be equal to B3. Okay, because they are equal. So when they are equal, their components can be equated. And when you are multiplying any number and A and B are collinear, if you are multiplying, then the scalar will be multiplied with all the numbers like this, like lambda A. Suppose you are multiplying with lambda A vector. So this lambda will multiply with lambda A1 I plus lambda A2 J plus lambda A3 K. Now one more condition comes when both are collinear, suppose, or parallel. So there is a condition when vector A and vector B, vector A and B are collinear. This condition, when we have to show collinearity, then also we can show this condition. Vector A and B are collinear or parallel. If they are parallel or collinear, they vectors, can write vectors A and B are collinear if and only if. Only condition is that there exists. This is the sign of there exists. I told you this is the sign of there exists. There exists a non-zero scalar, non-zero, non-zero scalar, non-zero scalar lambda such that we can write vector B is equal to lambda times vector A. This is the condition of showing the collinearity or parallel vectors. If one vector can be written as a product of some lambda with the other vector, then we can say that A and B are collinear vectors. And if you will convert this into the components, because vector B is what? B1I plus B2J. So if you will put B1I plus B2J in terms of components, B2J plus B3K, substituting the value of B in terms of components, and lambda into A1I, A1I plus A2J plus A3K, A3K. Okay. Then now you can see these are equal. So we can equate their components. As I told you that here you have seen that here you see this is the condition when A and B two vectors are equal, their components can be equated. So the similar condition is coming here, but with the product of the lambda. So lambda A1 is equal to lambda A1 equal to B1. This lambda A1 will be equal to B1, and lambda A2 will be equal to B2, and lambda A3 will be equal to B3. So we can write as B1 can be written as lambda A1, and B2 can be written as lambda A2, and B3 can be written as lambda A3. And if you will see lambda, this we are getting B1 upon A1, B2 upon, find the lambda from each equation, you are getting B1 upon A1 is equal to lambda. Similarly, B2 upon A2 is also equal to lambda, and B3 upon A3 is also equal to lambda. Okay. And after 4 minutes, the meeting will end, and then you have 10 minutes break, then come back. Now they are equal. So therefore, vectors A are collinear if their ratio is equal to some constant. We can say that thus the vectors A and B are collinear if and only if, therefore vectors, can write vectors A and B are collinear or parallel if and only if and if you have the ratio uh, B1 upon, if and only if you have ratio, I'm writing here B1 upon A1 is equal to B2 upon A2 is equal to B3 upon A3. B3 upon A3 is equal to lambda. Lambda is non-zero constant. That is, lambda is non-zero constant. Non-constant. Okay. So we can prove now. We can take the example. One question we can take. We have 3 minutes. So I think okay, so 3 minutes. You can write the question. You can try. You can try it. 10 minutes. Take the screenshot. Otherwise, I'm going to the next page. Example question is, you can note down if vector A, you can try in the time, vector A is equal to 3i minus 2j plus k, and vector E is equal to 2i, vector B is equal to 2i minus 4j minus 3k. Find, just you have to find very easy. You have to find modulus of magnitude of A minus 2b. First question. The third example. Example 4 also, for what value of A, for what value of A, vectors 2i 2i minus 3j plus 4k and ai plus 6j 6k are polynomials. These two you try in 10 minutes, then come back to the next class.